Sure.
Hello, everyone. Welcome to the last NAGROM seminar of the spring. It's a great pleasure, a real pleasure to introduce Professor Alessandro Veneziani from Emory University. And Alessandro is going to talk about the role of applied mathematics in the design of coronary stents. So it's a great pleasure to have Alessandro. So, Alessandro, the floor is yours. Thank you.
So first of all, so by the way, I'm connecting also from my cell phone, so I can see exactly what you see. So, so first of all, thank you for inviting me. It's a great pleasure to be here with so many friends, and I understand that I am the last before summer, so I hope this will be quite enjoyable talk where basically I know that the main topics is model order reduction. In fact, I am a user of model order reduction more than probably a developer, and I'm happy to share what we have been doing in a specific field like coronary stents, and what may be the role of applied mathematics, in particular model order reduction for next generation stents. So probably in this talk you will have more questions than answers, but this is good because it's just before the summer, so you have a lot of time to think, and and maybe I'm happy to receive answers to the question I have, and there are so many. So first of all, I want to introduce the group of people kind of involved in the research I'm going to present. First of all, so my PhD student Erwin Martinez, he graduated last year. Now he's in Denmark, Aarhus University as a postdoc. But part of this research is based on what we did together. Imran Shah is a biomedical engineering student at Emory Georgia Tech, and then Ben Yellin, Jachi Yang, Leonardo Molinari are PhD students here at Emory in mathematics, and then Jimena Martin Tempesti is she's a postdoc working on an NIH project. Then I want to thank many people. I represented here some of them. In particular, you know this guy, and you know probably this guy, Omer Sant, Ryan, Francesco Ballarin, also Gianluigi Rozza. Definitely, without, I think I can point out that without Francesco, many things I'm going to present would not would not be possible. And yes, the grant. This is one grant with the NSF. With Ryan and Omer, and then an NIH grant, an R01 with Lindsay Brooks from Georgia Tech. So I'm really lucky because I have this large group of people in different projects working together. So I want to use coronary stents as a case study in applied mathematics, scientific computing, and I will show you that since I guess this is a community of mathematicians, you may be surprised to know how poor mathematics was used so far in the development of some specific stents. Actually, not enough, in my opinion. So I don't think I need to convince you, but I use the same talk in less mathematical oriented audiences. And but I want to point out that with better mathematics, not only we can improve the current stance, but some failures in the past could have been avoided. But while I was doing this and I was preparing the outline of this talk, I realized that for every point I had a good quote from Led Zeppelin. I hope you know Led Zeppelin. If not, shame on you. About everything I wanted to say. So I will start introducing bioresorbable stents to show you how what was supposed to be a great and easy success on the market eventually turned out to be a failure. So not all the glitters is gold. And then also how in developing tools for bioresorbable stents, and not only we get to the to the necessity, to the need of reconstructing patient-specific geometries with the footprint of the stent. And this was a very challenging story in my unfortunately quite long research history. So been dazed and confused for so long. Then I want to point out what is the washer stress. This is a very biomedical engineering concept, and is a very important biomarker, say, from the biomedical, and important for the design of coronary stents. But yes, the interplay between stent and washer stress is not so clear. And then we need to understand also if we can measure instead of computing the washer stress. And then I want to focus more on the erosion, modeling of the erosions with numerical techniques like domain decompositions and model order reduction for the optimization. So what is a coronary stent? You probably are familiar with this, but let me show you. It's a very non-invasive operation where when you have a coronary artery with an occlusion, basically you can start from the femoral artery and then mounted on a catheter, there is this wire structure around the balloon. And the balloon eventually is inflated, as you will see in a second. And here is the catheter with the stent and the balloon. The balloon is inflated and the stent is left in place. This, okay, I'm going to say something about the material and the nature of this prosthesis, but it's a very consolidated practice in clinic in interventional cardiology. The first guy doing this on a human patient is Andreas Gruenzig. He was in Europe when he did this. And eventually moved to Emory. He was the director of interventional cardiology. Unfortunately, he had two patients, both related with fluids. One is blood, and the other is airplanes. So he was piloting a small airplanes, and he crashed out of Atlanta in 1985 with these small airplanes and his wife. So he passed away prematurely. But this is the first patient receiving a stent in human history. And this was 1977, and this is 2008. This is Spencer King, the godfather of interventional cardiology at Emory, and he's a good friend of mine. And he was still there, survived Andreas Gruenzig. He was still there, and it was a very successful story. But clearly, as for any innovation, there are some drawbacks. In particular, the fact, so leaving a metallic structure into the patient for basically lifetime is not necessarily a good thing, no? So in particular for young patients. So for this reason, originally stents were bare metal stents, only metal, but then this was creating a reaction from the tissues. So they invented drug-eluting stents. So stents with some covering of some drug to prevent inflammations. And in 2010, the Abbott introduced bioresorbable stents. So stents completely made of bioresorbable material, such that after a few, say, months or years, say long lifetime, 3 years, the stent is gone. The stent is gone, and this is good for young patients with an acute disease, not a chronic disease. Of course, if the disease is chronic, yeah, this is supposed to remain in place. But for an acute syndrome like an acute occlusion due to some non-permanent reasons, having a stent forever is not good. And this was supposed to be the great solution. So a stent made of material that can be absorbed by the body. And then, of course, there are many other shapes, many variations in the shape. So this is an imaging with the colors of a patient-specific stent, bioresorbable stent. And the struts of the stent are blue. The yellow is basically the wall, and the red is an inflammation of the wall. You may notice that there are many regions inflamed, so with inflammation. So there are parts that most likely will develop new thickening, so a new plaque, a new disease. Okay, so this is bad, definitely bad. And why is this happening? Sorry, I realized that in the movie was unfortunately covering what I wanted to show you. So let me just remove this. So the point is that in order oops, okay, let me eliminate this. Okay, in order the strut with the non-metallic material to stand the pressure that is around, could be around 15 atmospheres, to stand the pressure of the balloon, these struts must be thicker than regular struts for drug-eluting stents. And of course, these increased thickening, the thickness triggers some fluid dynamics pattern. In particular, so imagine this is the strut, the blood is flowing in this direction, and you see here some recirculation. Recirculation are never good when they occur over a tissue, because they create a pull and push on the tissue, on the endothelial layer, and generally this leads to inflammations. So the speculation is that this abnormal thickness is creating some biological reactions, and eventually the failure of the prosthesis, because then you have a reocclusion. Okay, so this is why I say not all the glitters is gold, because it was supposed to be a great idea, but with some drawbacks. Yet, if you go into the literature, so the bioabsorbable stents were withdrew from the market in 2017, but still after then, I found a lot of papers from clinicians saying that they are still a good idea, and we still need. So clinicians still think that a bioresorbable stent should be on the market, should be an option, and but they recognize that probably the first design was not enough understood. So all the complex sequence of mechanisms were not understood. And I want to mention this sentence: before initiating large trials in humans, we need to ensure that the technology is sound and that the trial design is flawless, based on solid science. Now, you see, based on solid science, I read based on mathematics, honestly. Probably I'm biased. Of course, I'm biased. But I think this is the missing part in what happened in the design of bioresorbable stents. So recently, all the companies try to reduce the thickness of the stent, so to go under 100 microns, exactly to avoid what I was pointing out. and still, this is an ongoing process. So I met the CEO of Abbott, I think it was 2017 exactly. And he told me, well, in 2020, we will have a new generation, but in fact, it's not on the market yet. So, but how can mathematicians, and in particular people doing simulations, can help in this process? And the first part is to provide a unique insight into patients. No, so we have patients. They can measure some data, and I will be back on this. But then, how can we do simulations? No. And for this reason, many years ago, this is 2013, but we started in 2010 with my I think one of the most important person I ever met in my professional life. So Don Giddens, biomedical engineer. He retired, but he's still very active. So we start in 2010 working on the reconstruction, patient-specific reconstruction of geometries with the footprint of the stent. And we found this an incredibly difficult problem. So this paper was published on JACC, Journal of American College of Cardiology. But honestly, when we decide to publish, I put a lot of caveats in this paper saying, okay, this is just the first attempt of reconstructing from data the footprint of the stent, and I was not completely happy. I had the impression a noise was dominating this process. So eventually it took basically 10 years to get a reliable and semi-automatic method to reconstruct geometries, including the footprint on the stent, amenable to numerical simulations. And why was this so difficult? I'm gonna give you some perspective. I just want to tell you that in 2012, this reconstruction was taking around 2 weeks for one patient. Now we take 2 hours, 2 hours and a half. So why is this so difficult? And you see the role of inverse problems in this, of course. First, we have one type of imaging to reconstruct the stent is not enough. So we are using 2 different imaging techniques. One is optical coherence tomography that is accurate, and an optical coherence tomography is basically this one. So so these are slices taken from a catheter and a camera mounted on the catheter. So you see probably from this square, you see the struts of the stent. Unfortunately, the catheter is creating a shadow. So we cannot cover 360. We can cover only, yes, almost 360, but not all of the 360. And okay, so the yellow is the wall and these squares are the strut. But this is longitudinal, so it's intravascular. So basically, the frame of reference of this imaging is inside the vessel, is not outside. So this is not enough, because basically, if the vessel is curved as it is, as coronaries are, we don't see this from inside. So for this reason, we needed also extravascular, so external procedures. So this is a digital subtraction angiographies where we can reconstruct the curvature of the vessel, so the real curvature. And then, but the other problem is that from the OCT, we can include the struts, but then the struts are reconstructed as points. So we get a cloud of points like this one, okay? But these points all belong to different portion of a strut. But which one? How can we define, how can we find which portion of the stent belongs? So each point we recognize as a strut to what part of the stent belongs to. And this is where we use, so we solve an inverse problem basically, and I'm gonna say something about this. But eventually from the internal imaging, so these are all internal imaging, so this is not including the real curvature of the vessel that we can reconstruct from digital subtraction angiographies. So eventually we have to map the reconstruct skeleton into the real curvature, into the real vessel. And from the skeleton, eventually we need to expand in a 3D structure that is coherent, is geometrically consistent. And once we have the geometry of the stent in place, by Boolean extraction, we can extract the lumen. So the lumen with the stent, so the stented lumen. So all this process now takes, as I said, half a day, say a couple of hours when everything is smooth, but let's say 3-4 hours when we have to do some cleaning. Using several libraries, SIGAL, Vascular Modeling Toolkit, FAIR for image registration, MNG for meshing, and eventually for the fluid dynamics, we have been using Glide 5. So let me say something about this process, in particular, the one that you may be more interested in as a mathematician. So the identification of the structure each point belongs to. And this is basically an image registration, but the novelty, if you want, of the trouble part here is that we want to start with a cloud of points and we want to end up in a polyline. Okay, so the registration is from a number of points into a set of lines with vertices and a connectivity table. So we developed this with my colleague Lars Rutotto, an image registration using FAIR. So we adapted the method of registration using the template of the undeployed stent. So the design of the undeployed stent, the skeleton of the undeployed stent as a polyline, and finding the map fitting into the points we obtained from images from OCT of the deployed stent. So once we do this, we used different mapping, rigid and non-rigid mapping. Eventually, we found that the sequence of rigid and non-rigid was very good, so we were getting good results. The second problem, big problem, was at this point to curve the view that we have, that is called the longitudinal view, the L view, into the real 3D geometry. Because as I say, the longitudinal view is in the frame of reference of the catheter, so it's not able of detecting the curvature because the catheter is following the center line. And then we had to map into 3D. So basically, we had this idea. Adrien Lefeu actually is working at INRIA now. This idea of performing a sort of deformation of a solid. So following, so to embed our L view in a cylinder, and then so you see this the L view and the stent, the skeleton of the stent reconstructed, and then using the center lines reconstructed from digital subtraction angiographies to map the current geometry into the real 3D view. So we solved a linear elasticity problem using the OCT as a sort of boundary conditions for some sections of each cylinder, and then some Neumann conditions and lateral conditions. So we did a sensitivity analysis to show that the parameters we were selecting were not so important for the final results, but in this way we were able of constructing a 3D structure, a 3D structure of the skeleton. Eventually, now when we have a 3D skeleton, this is not a 3D skeleton. This is already the the expansion in 3D. And this is where I learned that I didn't know enough about differential geometry. We started doing some naive expansion of this skeleton using the section of the stent, so the square, because the stent has a square section, to reconstruct a 3D geometry. And we found that it was never working until we found in this library Seagull, we found this concept of Neff polyhedra, which are a sort of Boolean representation of polyhedra, to define the solid around the skeleton. And in this way, we were able of reconstructing a 3D structure without self-intersections. If you did any 3D meshing, you know that on complex geometries, you know that self-intersection in an STL file are really a mesh killer. So in this way, we were able of, with Seagull, obtaining this 3D structure without self-intersection. And finally, by Boolean operations, we could reconstruct the stented lumen. So where you see the dots are the stent reconstructed from OCT, and this is the mesh we obtained for the lumen. You may be surprised that some red dots are out of the lumen, but this is totally correct because these are struts that were embedded in the tissue. Sometimes, so basically the reciprocal positions of the strut with the lumen may be outside the lumen but in the wall, or inside the lumen, or just attached to the wall of the lumen. So we may have all the possible relative positions, and eventually we can run simulations now, and we can compute the so-called wall shear stress. I'm going to give you the mathematical description. So for instance, this is one of our patient. The green is the struts, the red is the lumen, the blue is the wall. And this you see in this simulation, the wall shear stress computed in a patient-specific geometry, where you may notice that the strut are, and I'm going to be back on this, may trigger some particular pattern in the wall shear stress. And also, as I mentioned, as I pointed out here, so in this right panel, so here you see the streamlines induced by the presence of the struts, and here you see the Malapose stent. So this is a stent that, for any physical reason, during the deployment was not pushed by the the balloon, and so it was not touching the wall. And so this may create some perturbation, certainly perturbations in the fluid. And but this is not because the interventional cardiology was not good. It's just because this is part of the complexity of the operation at hand. So the deployment is, I was in the operating room during some stent deployment. The patient is awake and is very minimally invasive, but it's not, definitely is not not easy to perform a perfect deployment. So in this case, for some reasons, the balloon didn't push this strut against the wall. And this we consider this may happen all the time. But now, why we want to do this? Because we want to understand what is the interplay between the presence of the stent and the wall shear stress. Now, let me go back a little bit on the wall shear stress. So basically, if you are familiar with literature in biomedical engineering for cardiovascular disease, you see wall shear stress everywhere. So it's kind of the killer of all the possible things. So the wall shear stress, I think there are studies starting in the end of the 70s, early 80s by several great people: Morton Friedman, Seymour Glagov, Don Giddens, Bob Nerem. Bob Nerem was the founder of the Department of Biomedical Engineering at Georgia Tech, with Don too. Bob passed away a few years ago, just 3-4 years ago. And they realized that this quantity that is defined here, so the wall shear stress is, so imagine this is a Cauchy tensor in the Navier-Stokes equation. So basically viscosity gradient of U plus gradient of U transpose. So you take the normal component of this tensor, and as you know, this is not directed only in the normal direction. So we are multiplying a tensor by a normal. So we have a vector in any direction. So we subtract to this normal component the component that is really oriented along the normal. Okay, and this is the definition of wall shear stress. So it's the tangential component of the normal stress. And then typically people take the time average over heartbeat. So there was a good evidence that a low and oscillating wall shear stress, so in general, in the unsteady version of a low time average wall shear stress, is a proxy for intimal thickening, inflammation, and in general adverse events. So when you see that the wall shear stress is low, probably that part of the tissue will develop some pathology, some thickening. Now, is that true that bioresorbable stents for their geometry basically trigger lower wall shear stress, and so this is why they fail so much? So in order to answer this question, we wanted to take patient-specific geometries, exactly the geometries I want to show you, in order to confirm that wall shear stress is the killer. We wanted to process many data, and we are still processing. But consider that so far, since now we have this automatic technique, semi-automatic technique for reconstructing the footprint on the stent, we can really work with what we may call many patients. Okay, so of course this number may be small or large depending on the community. For a mathematician, this number is large. For a clinician, it's small. So for a biomedical engineer, it may be significant, say. In fact, we process 70, but I'm not allowed to show you the results over the 70 for some clinical reason related to the companies supporting the trial. But we are allowed to show 30 patients. But the good part of our automatic system is that we can process order of patients, say even more than 100, and more than 100 in this field. For this particular pathology is good for clinical studies, is good for clinical journals. Now, what we did was to reconstruct many patients, and now you see, we compare what happens on the same geometry with the footprint on the stent and without the footprint on the stent. Because the question was, can we conclude that we need the footprint is the footprint on the stent a game changer in the wall shear stress patterns? So here you see the wall shear stress patterns without and with. And you may notice, at least this to me is really apparent, that there are two different scales that are important to consider. One is the scale of the vessel, and you see that some patterns on the wall shear stress are totally related to the what I call the macroscopic scale, so the scale of the vessel, the curvature, some radius on some small occlusion or smaller radius. For instance, this red pattern is clearly related to that. But then the footprint on the stent is lowering the wall shear stress significantly. When you see the footprint, you see that basically the wall shear stress is going down. So there is also a micro scale, the scale of the strut of the stent. So this is just the first picture to show you what is the idea. And but we run these on the 30 patients I was mentioning. So a lot of steady and unsteady simulations. So we ran also on steady, and then we took the average. But we found that taking the average of an unsteady simulation, or taking a steady simulation as a surrogate of time average of the unsteady, these two different procedures lead to the same clinical conclusions. So, but anyway, we ran these on many patients to find from our evidence that the wall shear stress, if you, in average, if we reduce, if we eliminate the footprint of the stent, so we don't include the footprint of the stent, is generally higher than when we do the same computation with the stent. So we think, and in particular now we are I'm not going to these details. This is really clinically oriented to show that what is clinically considered a low wall shear stress, so less than 0.5 Pascal, was so the region in the stent with a low wall shear stress was significantly higher when we introduce the footprint on the stent. So this to conclude that in applied mathematics, now we have the tools to go into the clinics, so go into clinical trials to perform a systematic analysis of the wall shear stress with the footprint on the stent, so including the stent to understand how the presence of the stent may trigger inflammations through the quantification of the wall shear stress. And these are all other statistical evidence, for instance, how the macro scale, so I say the curvature of the vessel may have an impact, and in fact, lower is the curvature and lower is the wall shear stress. But in any case, and similar with the tortuosity, but in any case, there are some outliers in this analysis showing that we need the footprint of the stent. So yes, we definitely, the conclusion was yes, we need a footprint on the stent. But at this point, I had another question. The question is, but why should I use should I use CFD and numerical analysis? So a biomedical engineer may say, why we don't compute the wall shear, we don't measure the wall shear stress, okay? We take data and we try to measure the wall shear stress directly in patient. So I'm part of a very nice team with this NIH project where we are trying to measure the wall shear stress. So I'm running against myself, against the mathematicians, to see what's going on. But I think it's good because we find some interesting results. So basically, this is an experimental setup with ultrasound methods, which are probably the cheapest for clinics, trying to extract from velocity data from ultrasound the wall shear stress. So we say that the wall shear stress depends on the gradient of the velocity. So the idea is, you see here, so there was an inlet. This is a stenotic geometry, like a coronary artery. This is a catheter with a tip for ultrasound measurement. We were pushing water from the pump, and what we did was, okay, we reconstruct CFD. We run CFD to have a ground truth for the wall shear stress, but also we use the data to do numerical differentiation to compute numerically the wall shear stress from the measures. So what I found is what they were doing in the literature was really, say, inaccurate for doing this. So basically, of course, there is a lot of denoising, but probably, I mean, these are all technicalities for biomedical engineers. But what we found is that what they were doing was basically an assumption that the flow is pretty much always a sort of Poiseuille flow. And then they were using from the measures of velocity, they were dropping non-Poiseuille components of the flow to reconstruct to compute the wall shear stress. You may think that this is so this Poiseuille is a crude approximation. As mathematician, I was saying, come on, this is a non-cylindrical geometry, so there is no way a Poiseuille formula could apply here. But this was not really the problem. So here you see a comparison between computational fluid dynamics, so the black dots. You don't see the green lines, but there is a green line under the black dots. And then we introduce a pseudospectral method. So what I suggested to do, we suggested to do with Jimena was to perform a Fourier approximation of the velocity. So using Fourier and then to perform a differentiation of a truncated Fourier series. Because I was thinking this was much better for the reason I'm going to show you. And when we have no noise, so basically in the absence of noise, the wall shear stress reconstructing by pseudospectral, Poiseuille, and CFD with all the numerical approximations are pretty much the same. Of course, when we have real data, we have noise, and the noise is affecting velocity to the point that fine difference formulas, because after all, Poiseuille is a fine difference formulas, were really affected by noise, as opposed to the pseudospectral approach. In the pseudospectral approach, we naturally cut the noise because the noise is basically non-systematic, so it's a white noise. And so it's high frequency. So we cut low frequencies. We cut so we pass low frequencies. We cut high frequencies to the point that our pseudospectral approach can follow and identify the profiles of the wall shear stress we compute with CFD in a much better way. So we are happy. So in fact, it's possible. I mean, theoretically, it's possible using this pseudospectral approach to have a good approximation of the wall shear stress from measures. But when I got to this point, I had this idea, and then I have no slides for this because we are working on that. So the idea is why don't in this approach we are using data and then we perform an approximation of the wall shear stress based on data. But the next step is to do data simulation. So to use a model order reduction to identify the best boundary conditions that typically we don't have. We have here experimentally, but not in clinics. So to solve a control problem. So what we are doing now is identify the boundary condition that fits the data, solving the Navier-Stokes equations. And then at this point, once we do this, the wall shear stress is computed from CFD. So using the subroutines we have in our CFD code. So we are working now on this idea, and this seems pretty good. I'm having a problem with Arbenics. So Francesco, I'm gonna ask you help very soon. But I think the first results were pretty good in very simplified geometry. So data simulation probably will be, so I said we can use measures to compute the wall shear stress, so to measure the wall shear stress. So to have, without using CFD, I think the best way is to do model order reduction to perform data simulation and eventually to have the best possible approximation of the wall shear stress. So I see an important role to model reduction or also to physical informed neural networks in this space very soon. Okay, so let me go to the last part of my talk. So this is a book published in 2018 about bioresorbable scaffolds. And in this paper, I like this sentence, studies thought about the limitations of animal models. When I talked to the CEO of Abbott about bioresorb, he told me they used only animal models, but clearly animal models have many limitations. So, and I was happy, and I was pretty sure to find a lot of mathematics in this book. And no, I didn't find. So I found only some. This is a table of content of this book, but there is a minimal role to modeling. And I think this is an error, as I said. This is a big mistake, from not only from the scientific point of view, but also from the industrial point of view. So what I'm going to show you is two examples. One is how can we do a modeling of the erosion. Now, this is very simplified setting. So I want to model how the strata are eroded and they release material, magnesium in particular, into the lumen. So the red is the lumen, the blue is the wall, and the green are the struts. And I wanted to study this problem all together, okay? So to see the erosion. And this basically means that we have a Navier-Stokes equations in the lumen, and then we have some advection diffusion reaction, or advection diffusion, or only diffusion in the strata, in the wall, and in the lumen. In the lumen, we have U is the velocity of blood, so we have advection diffusion. Then we have only diffusion equation. So this is a very simplified erosion model. Of course, I know that with more species involving so multi-material strats, these equations are really simple, but this is just a starting point. So we need to solve a problem for Navier-Stokes, and then in the concentration of magnesium and the other material, but let's say one material of the strata in the lumen, advection diffusion, in the strata, purely diffusion, and in the wall, purely diffusion, because basically convection in the wall is minimal. Okay, so we wanted to study this problem, but consider that all the constant and we have Robin boundary conditions to model the Fick's law for the erosion, and also continuity of fluxes. So all the constants are different. So this problem is basically advection diffusion reaction, but with discontinuous coefficients. And the problem is well posed. Yes, this is not a difficult thing to prove. But numerically wise, how do we want to simulate this? So we decide to use a domain decomposition procedure where we solve, let's say, the lumen, assuming to know the boundary conditions on strata and wall. Then we solve the wall, assuming to know the boundary conditions, and then we solve the strat. So iteratively, we do a domain decomposition approach. So let me show you how it works. So we have a lumen problem. This is already on the time discrete version of the problem. So chi is 1 over delta t, basically. And then here we have diffusion, convection, assuming to know, this is iteration k plus 1 at a given time instant, assuming to know from the previous iteration the concentration in the strata in the wall. Then once we know this, we move to the wall, and we use the concentration we just computed and the old concentration in the strat. And finally, we solve the strats using the lumen concentration and the wall concentration in the previous iteration, and then we do a relaxation step. Of course, we can run this in parallel like a sort of Jacobi method, but let me focus only on this sequential approach. So, okay, it's possible to prove that this domain decomposition is convergent. Yes, it's possible. It's a classical argument. You can prove that basically the sum of the iteration errors is bounded by the initial guess, but basically when k tends to infinity, because we keep iterating, k is the number of iterations, this bound still holds, and this means that each term on this series goes to 0. So we have a convergence, but without convergence rate, there is no convergence rate estimation. So I was pretty sure to have some, sorry, but for some reason now it's stopped. I don't know why. Okay, so let me move manually to the previous, to the next slide. So what I was not prepared to see is that the number of iterations is independent of the mesh size. Okay, so you will see now it's just for some reason it's uploading. So it's independent of the mesh size. So I was not expecting this method to be optimal in the sense of domain decomposition. So the number of iterations is not affected by how fine is the mesh. Okay. And of course, I wanted to understand this process. And let me go to what we did many years ago with Alfio and Paolo Zunino. where basically in a case where we have only two domains, so only wall and lumen, so we were not introducing the strat, we were able of using Stekel-Poincaré operators. So basically, if you're not familiar, Stekel-Poincaré operators are a representation of the problem as an interface problem. So basically, we rewrote the problem on the interface using these differential operators. And eta is a function. And eventually, we found that the domain decomposition method we were using is basically a Richardson preconditioned Richardson iteration. So for this equation, so we have rho k plus 1 minus rho k. The operator SL plus SW, so the Stekel-Poincaré operator for the problem, was preconditioned by only the W part. And it was possible to prove that all the constant for these operators are independent of the mesh. So using some theorems on preconditioned Richardson, was possible to prove that yes, the iterative method is optimal, is independent of the mesh size. Okay, because basically this operator, all the features of this operator are independent of the mesh size. When we try to export these to this case, so when we have another domain, and honestly, I completely underestimated the complexity of the situation. So honestly, so okay, so this is a theorem that provides the basically the theoretical basis for this approach. So to recast the problem into an interface problem and eventually show that the domain decomposition method is a preconditioned Richardson. I'm sorry about these problems I am having, but I hope it's uploading now. Is coming up. The next slide. So I was saying that I had, okay, so this is the theorem. So when you have an operator, Q1 is continuous, symmetric, and coercive, Q2 is continuous and coercive, and we found that this continuity and coercivity were independent of the mesh, then this preconditioned Richardson operator is convergent. And since all the convergence depends on the coercivity and continuity constants, and these constants are independent of the mesh, the method is optimal. So when we got to this case, situations were much more complicated. So I had to introduce a lot of auxiliary operators in the lumen, in the strat and in the wall, to find that our basically all our problem could be written as a Stekel-Poincaré, not equation, but in this case, a Stekel-Poincaré system, because now we have 3 interfaces, not one. Lumen strat, lumen wall, and strat wall. And after some work, we were able of proving that in the structure of the, so we have now a Stekel-Poincaré matrix for the 3 interfaces. And we were able of proving that in this Stekel-Poincaré matrix, there are some components that are symmetric and uniformly symmetric and coercive. And in this way, what I found, unfortunately, is not what I was hoping to find. So basically, I was hoping to find that the precondition of in my scheme is basically a symmetric and SPD operator. Unfortunately, is not symmetric. But what I found is that basically is the perturbation. So there is a symmetric part, SPD part, plus a low rank perturbation. So our, in this case, the preconditioned, the domain decomposition method in terms of Stekel-Poincaré equations or system is, yes, is a preconditioned Richardson, but the preconditioner is not symmetric, but is a low rank perturbation of an SPD preconditioner. So now this is not a theorem. I don't have the theorem, but my argument is the reason why what we found, and this is the inverse of the preconditioner, so is the inverse of the SPD preconditioner plus a low rank perturbation. So the reason why our method is mesh independent is probably because this low rank perturbation is not affecting the spectrum of the preconditioned operator to change the mesh independence that I would have with only this term. So basically, this term is making our preconditioned regions on practical because he's making as a domain the composition scheme, and is not changing the spectrum of the optimal preconditioned iteration, at least not to the point that we see any mesh independence, any mesh dependence. And this is really good for us because even if we have a very fine mesh as we need, apparently the number of iterations is not increasing. It's not a theorem, and I have to disclose I'm not a numerical linear algebra person. So any numerical linear algebra person who may prove that yes, no, we can prove rigorously that the spectrum is not affected. So this is just an argument, is welcome. For me, this is still an open problem. Finally, and these are terms on so these were simulations on more realistic geometries, more realistic design of stents. We use first on simplified stents, but we are working on more realistic geometries of the stent for the erosion. But finally, and this is my last part, it's going to be probably more interesting for model order reduction, is this question: if the wall shear stress is so important, and the size of the struts is important. I mentioned at the beginning that probably the abnormal struts, size of the struts is triggering inflammations. What about the shape of the strut? So I got this question. Honestly, this is not a clinical, this is not medical, biomedical engineering. Nobody asked me this question. It's just me. I was thinking, but is that possible to find a shape of the struts that can control the wall shear stress? In order to answer this question, and I have just very preliminary results, and I don't know where I'm going with these results, but I'm happy to show you these results, was to run some simulations, and I used 3 possible shapes basically as preliminary results. So now what you see is the profile of the vessels. I'm solving axis symmetric Navier-Stokes here, just to simplify, to work in 2D, using these 3 different profiles. So these are planar struts like we have now. These are the struts with an extrusion, and these are struts with an intrusion. And I wanted to see what is the profile of the wall shear stress on the tissue, so between 2 struts, and after downstream the struts. So the blood is flowing from the left to the right. What I found is here. So here you have the flat is red, the blue is with the extrusion, and the black with an intrusion. And honestly, I found that the profile of the wall shear stress are not trivial, in the sense that, in particular, when I have an extrusion, I have a reduction of the wall shear stress, and I was expecting this, but I was not expecting an increment of the wall shear stress downstream. So apparently downstream, the presence of an extrusion increases the wall shear stress, which is a good thing, by the way. So this means that it's possible, and there is no idea like that in the construction of stents. It's possible that so creating different shapes in the struts of the stent and differentiating depending on the flow, the direction of the flow. So creating shapes with an intrusion here, and an intrusion would increase, is the black one, so increase the wall shear stress. But an extrusion in the last strut, for instance, so creating an orientation in the stent may control the wall shear stress. Honestly, this is just mathematics. There is nothing. I don't have any clinical proof. I don't have any benchmarking for this. It's just what I found running simulation. At this point, using Arbenics, of course, I started so the next question was, okay, can I identify the optimal shape? So I use this probably this requires a lot more of work, because I use model order reduction, so POD, to move the geometry, so to create a parameterized solution for the geometry. And for the optimization, I didn't use any gradient-based technique. I used a derivative-free library, a trust region method based on this library called bounded optimization by quadratic approximation, just to see what I get. But the functional I used was not a kind of local functional. This was just a functional taking the Washer stress in all the regions of interest. So integrating along the region of interest. So this functional could be refined. I think we can find a better functional. So what happened? No, this was just to show you that, and I kudos to Francesco Ballarin for creating such a tool like Arbenix. Basically, this is the definition of the Washer stress, and so this is a Python code I used. After Arbenix to run to find the optimization. So what I found is okay. So this is just a flow chart to see how it works, and I found that for all, so my optimal approach found basically to control the Washer stress. So the best is starting from different initial guesses. I found that starting from two different initial guesses, I found basically the same solutions, and these solutions tends to be flat. Yeah, so maybe I was wrong, but maybe at least for this preliminary computation, flat is pretty much the balance, keeping all the different regions of Washer stress overall with an integrated functional at best. But this is for this particular functional. Of course, working more strictly with clinicians and manufacturers, maybe this is not the best functional. The interesting part is that I found the same solution starting with two different initial guesses. When I start with this is the intrusion part. This is extrusion. This is flat, extrusion, intrusion. I found another solution which is suboptimal. So this means that there are multiple solutions, and at this point, and as expected, I would like to also to have a little bit of more insight into the analysis of this problem. So it's possible to understand better at the theoretical level the nature of this problem, to understand better how can we eventually identify the optimal solution, the best solution, not to get stuck in local optimal. So this is the solution I found using these only. So this is the non-optimal solution. So this is optimal. This is a local optimal. But in case also this local optimal found this different role for the last strat, and this is a concept I explore. I don't think that manufacturers have this idea that a stent, but if you think about physical problem, is not so strange. So a stent for now is produced without a direction in mind. So they can place a stent in one direction, the other direction, but maybe the Washer stress and using POD, model order reduction, may help a lot in this. Maybe the Washer stress may benefit in a shape optimization with the direction, including the direction of blood flow, the main direction of blood flow during the heartbeat. Okay, so I think you know this, but yeah, I think you know this. We're going to run this conference with Traian and Omer. We are co-organizing this conference at Emory in fall, October 13, 15 in Atlanta, the best part of Atlanta. So All My Love is the last song of Led Zeppelin. I wanted to mention. The good part of Atlanta, you can travel easily to Atlanta from everywhere in the States and around the world. So I hope you will be interested. And if you're interested in this workshop, ask Traian, not me, because because Traian is much better than me in organizing events. Okay, so when I started working more closely with doctors, I learned that there is an area of medicine called translational medicine. And then years ago, I was visiting doctors in San Antonio, in Texas, and there was a doctor with me, Dr. Bob Taylor, and he introduced me to these doctors. They were scared by the presence of a mathematician, but he said, "Don't worry, no worries. This is a translational mathematicians," and I think it's a nice definition. So that area of research, when you really bring the great theoretical development, and I know that here in this audience there are great people working on developing new methods. I feel that I'm not at this class, but I'm kind of translation. So I'm happy to bridge all these innovations for the benefit of human health and longevity, if you want. In particular, mathematical models and numerical methods are important because they basically, numerical models to me are always a great way to filter the noise in the data. The noise is not solving the equations, the models it does. So that part of the data that are not solving the equations can be filtered by models to reduce noise, like pretty much we showed in the Walsh stress measures. Definitely, model reduction is a breakthrough. 10 years ago, but 15 years ago, I would say, I was envisioning many things we could do solving inverse problems in patient-specific settings, but always my concern was computational time. We are not going to do this in timelines that can fit into clinics. When I started learning from you guys, from people, many of you, what is model reduction, I immediately realized that this was the missing part 15 years ago to bring shape optimization, solving inverse problem, data simulation to the bedside, to the operating room. And okay, highly automatic tools is always critical. Okay, so I think that in the book I was mentioning about bioresorbable scaffold. They were basically, and all these papers, they were mentioning a missing part. So the some missing tool in the development of next generation stents to get flawless. They say flawless, to get to go beyond the animal studies. And definitely I think that the combination of model-driven, data-driven, like we do in model order reduction, is the missing ingredient. Just if you want buying Stairway to Heaven, just to keep mentioning Led Zeppelin. Thank you for your attention. And yeah, I'm happy to take any question.
Beautiful talk, wonderful talk, Alessandro. Thank you. I really appreciate. I really liked it. Okay, very. So it was inspirational. So you might get questions or maybe answers. I don't know. We'll see over the summer.
Yes. So you if you have an answer to my questions over the summer, please. I'm hungry to have answers.
Okay, or more questions. So who knows, right? I mean,
or more questions. But in that case, you answer. I don't answer.
Okay. Well, this is funny. Okay. Well, so any wonderful thought. Thank you. So any questions for Alessandro? Do you guys have any questions for Alessandro? Thomas, yes.
Hello, Alessandro. Thank you very much for this so nice talk. Quite interesting.
Thank you.
Well, I have a rather technical question, but it's by curiosity. Is in your domain decomposition iterations? I mean, you have on one side you have a convection diffusion problem, no, within the artery, and you have pure diffusion problems in the stent and the wall, no. So my question: when you update the domain decomposition, do you, how to say that, keep iterating perhaps in the convection diffusion part and free somehow the solid parts, or do you iterate in the same way? I don't know if it can be.
So let me go back. So basically, no, we solve Navier-Stokes at the beginning of each of the domain decomposition iterations, and then we freeze the velocity, and then we focus on this problem, because this is supposed to happen at the same time step. So this is a time discretization, and there is nothing about the time step in the notation, because the notation is terrible already. But yes, so this is supposed, so the time step is frozen. And what one of the simplifying assumptions is that the concentration is not affecting the flow. Yes. So if this is your question, so we are assuming that the flow is occurring independently of this concentration, which is a simplifying assumptions. Going back to the years, so 20 years ago, when with Paolo Zunino and Alfio, we were studying this problem. Eventually, we found that it's pretty reasonable assumption. But at that time, we were talking about low density lipoproteins. I think that it may be work also for the material released by the stent. So the blood flow is not significantly affected by this material because basically it's flushed away rapidly. But yeah. If we assume that the blood flow is affected, yes, we should have an additional Navier-Stokes solution after in the domain decomposition. Definitely, yes.
I was rather thinking at some kind of time evolution approach, but it is purely steady, you know? Okay.
Basically, the domain decomposition. So the problem we are solving is unsteady, but the domain decomposition occurs at each time step. So it's basically unsteady, and this is a way also. So one since you can appreciate some technicalities. So for these for the strata we have only Neumann or Robin interface conditions. So if you want Neumann boundary conditions, so per se this is in the steady case this would be a problem because we have a Poisson equation with only Neumann conditions. So but since it's unsteady, no, I mean, we don't have this problem if the strat is against the wall and we can assume Dirichlet conditions on this portion of the strat. The steady problem would be more problematic for this case than unsteady. Yes.
Okay. Thank you. Thank you very much.
Thank you. Thank you for the questions.
Thank you, Thomas. Any other questions for Alessandro? So maybe I can ask a question or like a final question. So what is, to me, it was impressive, like the way that you put together all these different components. Like you started, it's a real problem, a tough problem. You started with the geometry, then you moved on to the numerics and the reduced order modeling and data-driven modeling. So
I'm lucky. I have a lot of good people around me.
And good taste in choosing those people. Anyway, so
yeah, that's true.
Okay. So so that's, I mean, this is impressive. Your group, I mean, you guys have done really nice work. But my question for you is like, really seriously. So my question for you is like in terms of future. So you've been working in this field for a while. So what do you think is going to be the critical component? I mean, like at the beginning, you emphasized the importance of geometry. Like towards the end, you emphasized computational cost, and then you moved into optimization. And so like looking ahead, what would be in your mind, what would be the next ingredient or the next direction or like the magic recipe?
No. Okay, so no magic recipe. I don't have any, unfortunately. I wish I had. No, let me put. There are two things. Honestly, this is a great question. Thank you for in terms of perspective. So I think that the development of model order reduction, or also I mentioned next time I want to go a little bit deeper in physical informed neural networks, which is a concept that I understand is controversial, and I think I understand why. But honestly, there are some things that I think may really be helpful. So I see that there is a great development of new methods and new ideas, and this is great. As I told you, to me, all these ideas are the game changer. Was missing 10 years ago. Really, I went back to some things I did in 2009 when I stopped because I said, oh yeah, no, okay, I see what I want to do, but it's too expensive. And now reconsidering some of those things because now with these tools and I see that is a good time. So I think that we need a strong effort in bridging to real applications because now the developments are really impressive in terms of methods and also some theoretical results or not so many theoretical results. So I would love, for instance, to have more theory behind PIN because I feel maybe I'm not good enough, but I feel some lack of theory in some things we do. But really on my book, if you want, what I want to do is to increase the effort in bridging these things to the bedside, to the operating room, to people who eventually may use all this stuff. But these as there are some troubles in this operation. So, for instance, when I met people from Abbott, and I just saying, but no computational mechanics, no. And I'm talking about 5-6 years ago, not 20 years ago. They didn't use computational mechanics, not model order reduction, not even computational mechanics, because they were thinking that no, there is the difference between the reality of their problem and what we can simulate is so the distance is too large, and is not true. So there is a cultural shift that we still need to working on to convince also companies that they need more and more advanced mathematics, including model order reduction, or if you want, neural networks, machine learning. But this is a challenge from our side of mathematicians. So we should not leave this mission to computer scientists. I hope there is no computer scientist who may get offended. I mean, neural networks are a mathematical tool. Model order reductions, these are all mathematical tools. So we need to guide people who are not mathematicians in using correctly these tools. They are delicate, important tools. In my opinion, around machine learning, there is a lot of enthusiasm, but also a lot of, not enough knowledge in the use of these tools. And we mathematicians need to drive the process. These may be excellent tools, but if they use well, of course, like everything. And honestly, in my experience, and I'm talking about an experience of a mathematician who was also in classes of entrepreneurial activities, because I have my own company and I had to be in classes and listen to lessons in lectures on entrepreneurial activities. I found that people are following ideas without enough knowledge. So we need to drive this process, this translational process, with a strong mathematical background always. When I see lack of mathematical background, I see failures. And this is, to me, is one of the most urgent things. Don't let people think that machine learning is, oh, I can replace difficult knowledge of partial differential equations with this neural network. I think this is not going to work. And is a bad thing.
Yeah, I agree.
After all, one of the nicest paper I read on neural networks is when they were proved that the sort of Weierstrass-Trianon for polynomials for neural networks. No? So they are a dense set of approximator for functions. And most of people using neural networks don't have an idea how important this may be. But we have this idea, and I think we have to drive this process. So this is I see a lot of great developments from the methodological point of view. I urge that we mathematicians do the current translation, and we don't let people misuse these tools. Of course, when we have libraries like Arbenix, EasyRB, or other libraries, people may think, okay, now I do this and that. Arbenix, no. Arbenix is a great library because you need to know exactly what you're doing if you want to use it. But then, of course, it's good that these libraries can be used by as many people as possible, but we need to do an effort to have educated users.
Yes.
And this may be a success in the translation.
Thank you. This was a very nice. This is a very nice answer, and this is the type of things that we're looking for. And so, thank you, Alessandro. Anyway, so any questions for Alessandro? Any other questions? If not, once again, thank you. It was a wonderful talk.
Thanks to you.
Excellent talk. And this is the last talk in our spring session. We'll see everyone again in the fall. we'll put together the full schedule, and we'll let everyone know, and hope to see as many of you there as well. So see you.
Thank you everybody.
Bye.
Bye.
Bye-bye.
Thank you. Bye-bye.
Thank you.